Check, check. All right. Welcome, everyone. Thanks a lot for tuning in again. We're in week 16 of the stream, which feels pretty cool. I'm just going to get set up. Got my 20-minute break timer set up now. I'm a little bit sick, unfortunately, so my voice might sound a little bit different. Hopefully I don't cough too much or whatever, but yeah, thanks for being here. As always, we're here to do some learning about operating systems and stuff. What was I doing last time? I was working through lab 1 of this MIT class last time. And had basically completed the main parts that I was interested in. Right, we did this backtrace last time, and that was pretty cool. And now I feel like moving on to the next one, which is memory management, which is something I don't know very much about. And so hopefully this will be a chance to really write some code or something like that. So yeah, I'm just gonna do a quick message in the chat to say hello. Okay. So how's my build doing? I think maybe make sure my build is all set up. I just tested it before starting here. So now we're on the lab 2 branch, make Kimu. I think this is what it, oh wait, shit, I just realized my display size is way too small. I forgot to make it big. Okay. Hopefully that's bigger on the screen now. Yep, got this thing. Yeah. I'll try to make this moved over there. Okay. Clear out this thing, don't save. Let me just get it back to a nice clean state because I don't know what files we'll be touching today. Okay, so let's begin. In this lab, we write the memory management code for your OS. 2 components: a physical memory allocator for the kernel, so the kernel can allocate memory and free it later. Working with pages, maintain data structures that record which physical pages are free and which are allocated. And how many processes are sharing each one? So there's some ref counting probably there. You will write the routines to allocate in free pages of memory. Second component is virtual memory, which maps the virtual addresses used by kernel or user software to addresses in physical memory. x86 hardware is MMU. Okay. Okay, got it. This is boring stuff. So we have some new files here. Memory layout, pmap, cnh, k, clock, cnh. Address of the virtual address space you must implement by modifying these files, or by modifying this file. Mem layout and pmap define the page structure that you'll use to keep track of which pages. Okay. Manipulate the PC's battery-backed clock and CMOS. Wow, what? In which the BIOS records the amount of physical memory the PC contains. The code needs to read this in order to figure out how much physical memory there is. That is interesting. I had not even considered that. Oh, what? That part's already done for you? Okay. Pay particular attention to mem layout and slab. Okay, maybe I should read through those. Excuse me. Okay. Gotta get to a clean space in my board in case we need some, yeah, some visualizations. Okay. Which parts of RAM are free? Well, before I even start, let me just do a quick run through of what the kernel even looks like now, because apparently stuff may have changed. Entry to S. So this looks all the same. Init, let's see. This looks roughly the same as last time. And then now apparently we're doing this mem init stuff. pmap.c. Okay. So our set. Some nice global variables. Okay. Interesting. Detect. So this is that thing they said that was already done for us. NVRAM read. It goes out to the RTC. Interesting. Huh, okay. So, yeah, there's some code already here. Minutes. Interesting. Okay, we have the panic. How does the panic work, by the way? Is that new? What is this? Interesting. Like, clears interrupts and re-enables them? I forget what that is. Okay. Okay. Yeah, there's a bunch of stuff. Apparently a bunch of full scaffolding for how this works. A bunch of stuff, whatever. Ooh, wow. How does the assert work? It's just a panic, okay. Okay. Oh. Sorry. Okay. Okay. Okay, I think I have a basic sense. What do we actually do? So physical page allocator, step one, because in order to do virtual memory, we need to be able to allocate memory for the page tables and stuff. And pretty much there's no dynamic allocation at all right now in the kernel, I think. Okay. Exercise 1. You must implement code for the following functions: boot alloc, page init, page alloc, page free. Also need to add some code to i386 VM init. As indicated, now just add the code needed before the call to check page alloc. Okay. What? Oh, wait, what? I'm already a bit confused. Am I missing? You add some code to this function in pmap.c, which I do not see. Am I? On the right, checkout lab 2, right? I am pretty sure I'm in lab 2. Yeah, I'm in lab 2. Okay. I don't know what that is about. So okay. Implement some code. Do some stuff in this thing. For now, just add the code needed before the call. So let me figure out, first of all, I don't understand what they're talking about. So this is the actual function, right? Maybe this is the new name of the function. Create initial page directory. Boot alloc. That's the thing I didn't do yet, right? Lab 2, your code here. Anyway, okay. Add the code just before this call. You probably want to work on boot alloc. Then this thing, then these other things. Check page alloc tests your physical page allocator. You should boot JAWS and see whether page alloc reports. Fix your code so that it passes. You may find it helpful to add your own asserts to verify that your assumptions are correct. For comments to modify those comments contain hints. Okay, and until manuals. Okay. Let's give this a try. I have actually no idea what I need to do. So they have a recommendation, work on boot alloc first. Let's just try that. Boot alloc. So the context here is that basically the first thing we're trying to do is allocate a page of memory for the kernel's page directory. Okay. And so they've already started working on an allocator for us. Wow, static variable. Sheesh. Okay. So they've, yeah, simple memory allocator only used while just is setting up its VM. Page alloc is the real allocator. Okay. And it said that eventually we get to these more legit ones. But for the moment, we're not. If n is greater than 0, allocates enough pages of contiguous physical memory to hold n bytes. Doesn't initialize the memory. Returns a kernel virtual address. Okay. If it is 0, returns the address of the next free page without allocating anything. If we're out of memory, bootalloc should panic. Only use this during init when before this thing has been set up. Okay, let's see how to do this. So you have some pointers to results. If not, next free. End. Interesting. What was the end thing again? The end of the BSS. The first virtual address that the linker did not assign. It was here. BSS is here, and it provides some externs. And so, like, apparently, we are just going from there or something. Let me quickly refresh on the memory layout. Kernel is mapped quite high, if I recall correctly. Yep. For whatever reason, we chose this physical address at the 1 megabyte mark, which I think is actually where it really gets loaded. Yeah, but virtually we're all the way up here. Yep. Okay. And so apparently we just start using that. Interesting. You round that up to a page size, and that becomes okay. So we're making this really dumb allocator right now. Apparently we just assume that the memory after the kernel is free. I think this is a bump allocator. It seems to just have a single piece of state and it can't free anything maybe, or at least can only do it in like one massive swoop for freeing the entire heap. All right, 20-second break. Give me 1 second. All right. So apparently it's a bump allocator, I think. And we can round up to the nearest page size using some bit math or some macro. Interesting. Type of A. Okay. Yeah, it's a bit harder to read than I would have thought, but okay, whatever. You have some macros for doing rounding, which is helpful. Allocate a chunk large enough to hold n bytes, and update next free. Make sure n free is kept aligned to a multiple of page size. So, if n equals 0, returns the address of the next thing. Okay, I'm just going to take care of that immediately. If n equals 0, return next free. Otherwise, so we're going to allocate a block even if the size is not aligned to page size. We're going to still manually like allocate that much, and then return a pointer to the initial block. So, okay, why is it returning null? Just for the compiler, I guess. Okay. So we're going to need some kind of like actual size. I'm just going to do this like kind of sloppily right now. Actual size. Because we need to take the n. Okay. And it's round up. I mean, it's let's see if I can figure out how this works. It casts it to a char pointer. Interesting. Round up to the nearest multiple of y is expected an expression. How is that not an expression? Does this compile? It compiles. Okay, I think my VS Code is just giving some false positives or whatever. So I'm gonna take this step by step very slowly. Okay, we had the n that's requested. We bump it up to the next page size. I think result is going to be next free. And then next free actual size. Return results. Is it confusing? Yeah, so we have, yeah. I think, yeah, what's the best order of this? So next free always points at the next free block, which is what we're going to return. So we can set that just immediately. We already know that we're going to be returning next free. The question is just, what does next free go to at the end of this function? I think this is approximately right. I have no idea how to test this. I have no idea to test if I'm actually correct, except for maybe stepping through some of this code and maybe even printing some stuff out. So I'm just going to take this chance to clear this out. So how do I print stuff out again? I was using cprintf last time. Where's this? Cprintf. Let me just do a quick test. Okay, I got my hello. Excuse me. Got my hello. So that means I'm in business to start print debugging. I'm going to move this. I'm ready to officially attempt to execute this first part of the code. Boot alloc. I'm going to can I print cprintf? Oh, two. Oops. Okay. Okay. Let me just do some basic verification that this is working. So we're on the first call. And so I am going to yeah, let me just next free. So we just initialized it to some variable. Let's say, now I just want to check this stuff. Oh, what? Okay. N is what? A UN32. I have no idea what the character code is for that. Actual size. Actual size. Next free. Let me just try this. Init next free. It starts off at this E thing. And let's see if that's consistent. How would we check this? Is there a BSS thing here? I actually don't really know how to check. Okay, so the BSS is here. Aha. Offset 680. I don't totally know if this will work, but because I don't. Yeah, that's not what's here. Well, maybe this is page aligned, but even still, it's at E. And page aligned, this would be D, so I kind of don't know. Yeah, anyway, I'm going to ignore that. I'm just going to take it for granted that the BSS ends at this E thing. We're allocating a page size. The actual size is just the same thing, and now we bump that up to the F. That looks right to me. It would be nice to have some way to do unit tests for this, but now's not quite the time for that. I think I'm just going to try to get this working. Unless there is some way to do tests? I don't know. Nope. Nope. Ink. Current. I mean, I don't really think so. Print format. User. Okay, yeah. Okay, I'm just going to manually test this right now then. Yeah, it'd be like really nice to just have some kind of like test harness thing where I could run this a bit more in an isolated environment. Yeah, I think like I would love to do that. It might take a bit of time and distract me from the stream right now. So I'm just going to do some basic tests and verify by hand like once. And so I'm going to change that from page size to 99 and observe that it gets rounded up all the way to 4K and it's the same. Yep, makes sense. Now I'm going to do what, page size -1, for example, just to run through some basic tests. Yep. The point being this should, I mean, yeah. I'm just going to add an assert at next free page size equals 0. The next free is what? Right, so one's a pointer. I guess, is this a good chance for u and pointer t? I think it might be, because we're trying to use a pointer as an integer number and just do math on it. So my assert didn't fail, which is good. Hey Andrew, happy Sunday to you too. Thanks for tuning in. So I'm going to do something to make my assert fail, just to make sure that's working by intentionally making that function wrong. Assertion failed. Nice. Wow, my Mac OS thing just popped up. Why is that? Andrew, I'm working on operating systems development, learning, basically. I would really like to be good at operating systems programming. So I'm just following this MIT class on operating systems. And I'm just kind of working on their exercises that they have. Eventually, I would like to build my own OS, but I'm not good enough to do that. So this is just what I'm doing in the meantime. Thank you. So I think I just proved my point. I just triggered the assertion failure. So that's good. I'm being a bit, I guess I'm proceeding a bit slowly and conservatively. I could move faster, but I'm just doing all these extra checks just to kind of make sure that I have coded this right, even though it's quite simple code. So now my next test would be like, I just discovered the channel through Serenity OS. Awesome, yeah, thanks so much for subscribing. Yeah, Serenity OS is a role model of mine, I suppose. I would love to also, I mean, not do something exactly like it, but also have some kind of like OS project of my own one day. So thanks a lot for checking my videos out. Yeah, feel free. Yeah, I noticed you joined the Discord too. Thanks so much. Working full stack for my job, but low level programming. Yeah, nice. Yeah. I work on electronics hardware, software that runs on like embedded systems during my day job, but I don't really do OS stuff ever. Although I do C++ at work, but it's super different from the stuff I'm doing now. Right, so this should round it up to 2 pages. Yep, so now we're a bit over 1 page. We bounce that up to 2 pages, and then now we're even here. So I am appropriately convinced that I've written this dumb bump allocator correctly. And I will take out this stuff. Okay, is that really it? That's interesting. So I mean, I learned something. I didn't. I mean, like writing a bump allocator is not that hard, but the question for me was like, where do we even start? And apparently, we're like using the kernel as a reference, and we're kind of just kernel did not assign to any code or global variables. I'm just interested how we can be sure that there's nothing in memory there. But apparently we wrote this linker script that guarantees this. I mean, we can see there's all these different sections and segments or whatever, and the BSS is really the thing at the very end. And just confirming also here, the BSS is the last section. I still didn't totally get how it's like this E address, how we can be sure of that, or like how we could, for example, like recompute that if we wanted to, but I think, yeah, that's just interesting. It's an interesting learning for me that you can use the kernel as a reference point, and you can, using a linker script, customize the different segments, and then also get a symbol to the end of the kernel, which is nifty. So maybe we update our diagram. So basically, why does it say physical memory? It says, I think that's wrong. It says virtual memory. So we have the kernel, and then just to keep this a little bit up to date, we have our boot alloc region. Why is it so? Why is there boot alloc region immediately after the kernel? Yeah, what was I looking at last time? I was looking at the kernel stack last time, and so somewhere within the kernel, there's like the kernel boot stack. And then right after that was, I think, the initial page directory page tables. Those were immediately after it. So just kind of documenting this. I don't know exactly where it is within the kernel. But yeah, I'm also gonna, yeah, I also want to start kind of like a to-do. I mean, I already have all these Kanban boards, but I was also uncovering so much stuff. So to do, use BS instead of data section for init kernel stack. So it stops taking space in the kernel binary on disk, for example. That's something we discovered last time, which is that the kernel stack actually currently occupies space on disk, which is kind of embarrassing. Okay, time for another 20-second break. Be right back. Okay. Let's move on. So now I did that. And now it's going to mem set that to 0, which makes sense. Recursively insert page directory in itself as a page. You don't have to understand the greater purpose of the following line. What? So we're inserting an entry into the page directory. So also to be clear, we are setting up a new page directory. We have this like really basic one. I believe that's still there. We have this extremely rudimentary page directory, which we were using just to bootstrap the system and move into protected mode. But it only has 2 mappings, and they're illustrated right here. This region down here, I think it's 2 4 megabyte regions. This one, they both point to the low 4 megabytes of physical memory, which is where our kernel lives. And apparently now we're attempting to again transition to the real, like, final virtual memory layout. And you might wonder, at least right now I'm wondering, like, why don't we just modify the existing page directory? Because we already have one, right? And it's like big enough and stuff. But apparently we're not doing that. We are really allocating more memory and creating a totally new page directory from scratch, which is kind of interesting. I don't totally get that. And so at a minimum, we're going to need that new page directory to have this mapping, this one that maps this high region of memory into the kernel, because that's where our kernel is, and that's where our code is executing from. That's where so much important stuff is. So at a minimum, we probably need to recreate this mapping. In itself as a page table. So what is this? User read-only virtual page table. Gotta be honest, I don't know what that is. PDX. It's just a shift thing, or... Interesting that it like clears out these high bits. Linear address, okay. So yeah, add virtual address. A virtual, what is a virtual page table? The kernel's page, which is that thing I was just no. Oh, this is that new one. Okay, I think, yeah. I mean, it says I don't have to understand it. It's like this, yeah, recursive, it's like pointing at itself somehow. Is this rounded down? No, it's a direct translation, actually. It's a direct translation to physical memory. So how do we know this thing is, does it matter that this thing is aligned to a page? That's kind of what I thought. a page table entry points to an aligned physical address. I'm not seeing any alignment guarantees happening here. So that's interesting to me, but anyway. Anyway, so we have this global variable thing. It's like a PDET, yep. Okay, whatever. Let me just check back in on the actual assignment. Is that, okay. Was that all that? That was all I needed to do for boot alloc, I guess. Then going here, okay. Allocate an array n pages, struct page infos. What is n pages? Okay, I see. I see, okay. Okay. Pages. Okay. I really need to learn the keyboard shortcut for go back. That would be a lot easier, right? So I can navigate through the selection. Okay. Allocate an array of that many page infos and store it in pages. N pages. What is this thing though? Ah, okay. This array to keep track of physical pages. For each physical page, there is a corresponding page info in this array. This is the number of physical pages in memory. I would love to see where this gets set and by who. Oh, this is probably that thing with like reading the hardware or something. It's like, yeah, it's this thing. This is that really low level stuff that figures out how much physical memory there even is, which gets printf'd right there. Apparently we can do some like IO calls to figure that out, and then piece them together maybe, or base mem. What is this? Okay, a bunch of stuff. Physical memory available. Let me just read that for 1 second. This much available. Base equals this thing. Extended equals this thing. Also, what? 131,000 kilobytes? What? Isn't that like over 100 gigabytes of physical memory? Am I being like slow? Like, huh, interesting. So I wonder what npages is. Does it tell us, or like, what is npages? I don't even know the type of npages. Size T. Is that? So apparently we have that many pages times the page size. Apparently that's how much physical memory we have. Divided by what? Megabytes? That seems more... Is that reasonable? 128 megabytes? This is like weird page size divided by 1,000. Total mem divided by 4, basically. Yeah, really, base, what is base mem? That's just this variable. And pages base mem. Amount of physical memory in pages, amount of base memory in pages. Okay, I don't understand the difference between physical memory and base memory, but whatever. I'm just going to assume that n pages is correct, even though, yeah, it really, 768 pages, right? N pages. Times 4K, which is the total number of bytes. Apparently I have 128 megabytes of space. Although, is that passed in the Kimu argument? I don't see it passed here, so I don't know who decides that 128 sounds like a very small amount of memory. 128 megabytes. Maybe I did that wrong, but I'm just going to continue. So we have all these like global variables, which are like really hard. I kind of want to just do like a big rename. I'm just going to do a commit. Okay. I'm going to open up my fork program and do it there because I kind of prefer that. Okay. That do what I want? No, that did not. That did not do what I want. Next free. Okay. Bump allocator. Okay, I'm just gonna take this chance to like rename like a bunch of these variables, which I hope should be easy. But just so I know, oh no, I did not want to. Yeah, that's annoying. I'm just gonna click apply. What did that do? Did that do what I want? I think so. I probably should have you know what, this is a bit of a distraction. Don't need this. Don't need this. This is all random stuff I did. This is all the change. Does it still run? Okay, I think it does. That was a little bit annoying. I didn't. Whatever. I'm just gonna not worry about any of this stuff. So kpages equals boot alloc npages. How do they do this? They just cleared out. They just knew the amount. Wait a second. No, I did this wrong. Allocate an array of npage. So I think I need to do this too. I'm trying to allocate. Yeah. And so realistically, I can maybe make a local variable that's like size t. I'll change this. Size. I don't totally know the best name for that variable, but I'm going to allocate that much, save it here, clear that out. I think I did this right. Nicholas, what the fuck, is this live? Yep, indeed, I am actually live right now. Thanks for watching. What gave me away? First time seeing me live. Well, thank you for joining. Now I'm in the same position. How do I test if this is right? I have no idea. I could go into the debugger and dump memory. Yeah, I have not really been in the debugger much today. Let me do that. What? Ah, that's why. Okay. Now I'm trying to break on mem init. Oh shit, but it's gonna panic. Okay. All right, let's quit. Let's move the panic line down. Now let's panic here. All right, let's rerun that real quick. Okay, let's just see what's going on here. That's exactly what I expected. Just for fun. Page info. 8. Okay, 20-second break. Be right back. Yeah, I guess I forgot to say it when I started. Yeah, this is me embarrassing myself live on the internet as I attempt to learn operating systems programming. So I'm actually kind of surprised that page info is that small. But it's really only, I mean, it's a pointer and a U16. And so that rounds up to 8 bytes, indeed. Because it's like 4 bytes for the pointer because we're on 32-bit, plus 2 rounded up because of padding. So makes sense. And so we can just independently do some math on the side. So that's kind of my expectation for how much page int this thing is. Okay, word. And then memset, right? So now, if all went well, k pages should be pointing at this like big ass block of zeros, basically. Does this work? Yeah. Like, this, yeah, I mean, what, how big is that number anyway? 256K. Kind of a lot. Anyway, I mean, it looks like it's like a ton of zeros, right? So I'm pretty confident my memset worked. I guess if I were like really smart, I could not dump the entire thing, but I could compute the end of that allocation. So what was it anyway? I asked, so we got n pages, they're each 8 bytes. We have, so this is the total amount of bytes. And then that I asked for, right? Boot alloc is going to give me like way more. But then we're not like aware of that, so we're just going to zero out just the amount we asked for. So I could, for example, determine what the end address is. And then I could go like, yeah, why not? Then I could like dump a bit of memory. Like 8 bytes below that or something. Okay, the interesting thing is it's like a ton of zeros anyway. So I'm not like, I was kind of expecting to see like a bunch of zeros and then like some junk in memory, but it's all zeros anyway. So I'm not totally sure if it's really working the way I thought it is. Nicholas, my goal today is to work on this MIT Lab 2, which is what I'm doing right now. I only have about an hour left in the stream, so I don't know how far I can really get, but I kind of, and I'm working my way through it. Yeah, I mean, I did exercise 1 just now. Now I'm kind of moving. Well, actually, no, I didn't. I'm still doing exercise 1. So maybe my goal is to finish exercise 1. I guess that's my goal, which is basically setting up enough to get, I guess, later virtual memory working, but the foundations of like a basic little allocator. This course is called, it's 6828 Operating Systems Engineering. I'm following an old one. I think there's like a newer one out there, but it uses RISC-V, which I'm not interested in learning right now. I mean, yeah, they're like, there's one from last year. So, yeah. Yeah, I would love it if you followed along with me too. We could check in on our progress together and form a little study group even if we have questions and stuff. Yep. Okay. Anyway, I mean, I think I might just move on. So, memset, I mean, yeah. So now that we've allocated the initial kernel data structures, we set up the list of free physical pages. And also just to be clear, so now we're allocating like actually kind of a lot of memory. Not a lot, but like in comparison to our previous allocation, which was only 4K, is it true that we just allocated 256K? That's the number of elements. That's the number of bytes. I think it is true. So we just allocated. Now we're just like we are really we're really doing it right now. We are, you know, we are allocating stuff in the boot alloc region. You know, this is not to scale. It's probably like this much basically, but we are using this boot alloc. Yeah. Andrew just joined. Yeah, the Discord is still pretty small and cozy. Only a couple people. I mean, I think we have about 25 or so people in there right now, but it's kind of quiet. So I would love if you wanted to come and hang out and chat about operating systems and stuff like that. Okay, so I think now I'm ready to move on to this next thing. So now that we've allocated the initial kernel data structures, we set up the list of free physical pages. Once you've done so, all further memory management will go through these page functions. We now map memory using boot map region or page insert. Interesting. Well, I got to be honest, I am glad I even made it this far. I always get kind of nervous about trying to do these exercises because I have no idea how hard they will be or whatever. But so far they've been like, you know, each little chunk of this exercise has been pretty approachable and pretty, I would say like kind of like baby steps and kind of very much hand holding, which is kind of the point because it's like for a class. And so I think one day it would be cool if I were able to do this without so much hand holding, but for the moment, I think I need it. All right. Now we've allocated the initial kernel data structures. Yep. So now we have all these structs that represent all of the physical pages. Let me just check again. It's probably important to know what this even is. Read only to user programs. So there's a free list. So each page info, I feel like it might be a good time to like visualize some of this stuff again. So we have this big long so we have this big long list of page infos. Make that like blue or something. Oh, what? And they are all sitting next to each other in this list. Apparently, like, they might even like point to each other or something. I kind of wanted that to like bend a little bit, but it's all okay, whatever. So they have pointers to other ones. Okay. And they have a ref count. The count of pointers to this page. So for every physical frame of memory, we are tracking this with this data, with the data structure. And really the key data associated with it is the number of references of how many people are mapping this page. And then as kind of like, you know, for bookkeeping more in the back end, we're keeping this linked list. And note that this is an intrusive linked list because we're storing the link directly in the struct. There's no way to allocate just a page info. You like always allocate the linked list with the entry, so it's an intrusive linked list, which is really common for kernel data structures. Anyway, okay, now that I kind of know what that is, after this is done, never use boot alloc again. Only use the page. Probably because, are we going to like reclaim? No, that's kind of dumb. I was going to say, are we going to like reclaim all that memory from the allocator? But we can't because we're literally using it for all these struct infos. So, okay. Only use the page out. I don't quite get the significance of this never and only. Like why is it such a big deal? But okay, we'll see. Only use the page allocator functions. Okay. Example hub here marks all physical pages as free. However, this is not truly the case. What memory is free? Mark physical page 0 as in use. So we preserve the real mode IDT and BIOS structures in case we ever need them. So apparently there's physical page 0, which is all this stuff like really at the bottom here in the first 4K of memory or something. The rest of memory is free, but also what? Oh, okay. What's it doing? It's going through all of the things. It's zeroing out the reference count, even though it already is 0, because that's what we did previously. And oh, interesting. PP link. It points it to this thing called the free list, which is what, the head of a linked list or something? I'm actually not next page on the free list. Interesting. And for every single one, we reassign this thing to, wow, interesting. So maybe I was kind of wrong. I don't actually get this pointer thing. I'm going to also simplify this diagram and make it shorter. So we have page, caps, page free list, which is like this global variable. So for each one, we go through and set the reference count to 0. I don't like, okay. So I kind of see. Wait a second. I'm still kind of struggling to understand this. Code marks all physical pages as free. Okay. I'll take that at face value and try to understand that. So page free list is a pointer to, for example, yeah, there we go. Okay. To a struct page info. It's like the head pointer of a linked list. For each one of these things, we take the link and assign it to whatever the page free list currently points to. Interesting. But like, what happens on the first one? This thing is it initialized to 0? Because it's static, or? I don't totally know. I would expect that it's actually not 0 initialized. So does someone else do that? Check page off. Okay, no. So, okay. PP link. So I'm not totally getting what's preventing this from just being like a junk pointer. Let's assume it's 0 initialized. Maybe we can even set a breakpoint or something. So I'm going to move our panic even lower. And I'll quit this, I'll rerun over here, and I'll breathe page in, oops. Continue, page free list. Okay, it's 0 for some reason, maybe because of the static. Okay. So let me slowly try to understand this. Okay, so for the first one, this pointer is going to get set to a null. Okay, I mean, okay. I think I kind of got what's happening on an intuitive level. This thing, it's like constructing a linked list backwards. So this thing points to null. And then on what? Then page free list now points to, wow, this is so confusing to look at it this way, but okay, I'm just gonna put the null. Okay, page free list was initially pointing to null also, or yeah. So now this thing points there, and then now this thing swaps out and points to this thing. That's just kind of what I'm reading. Let's go to the next one. Now this thing gets set to point to where this thing points, and then now this thing points to this thing. So confusing, but the arrows are like crossing in ways that makes this confusing. But basically, we are assembling a linked list kind of backwards, which maybe is the easiest way to do this. And so by the time we're done, linked list will point at the end, and each of these entries will point to the one before it. And so the first thing in the list is actually the last one in the array, which is interesting. All right, 20-second break to stand up and stretch and all that. Well, that's cool. So now I kind of get this. Yeah. So and these should represent free pages of memory. Okay. So when it says that it marks all physical pages as free, what that means is that every entry in the array is in the list. All the things in the list are free, therefore, yeah, they're all free. So we have a couple exceptions. Mark page 0 as in use. But also, like, what? So is this page 0? Like, is that how that works? Page 0, page 1? I guess so. Do not touch the physical memory corresponding to free pages. Corresponding. Interesting, okay. Ugh. So I'm still kind of trying to understand this. I mean, I get what's going, but now I'm trying to understand, what does it mean to have a page be in use? So, or like, I understand, like, is it the reference count or like, what, yeah. K pages. Pointers to this page for pages allocated using page alloc. So I'm not quite sure if I should be updating ppref here actually. Mark physical page as in use. So we preserve some whatever. The rest of base memory. Ah, interesting. Base memory. Then comes the hole, which must never be allocated, the IO hole. Then extended memory. Some of it is in use. Where's the kernel physical memory? Which pages are already in use for page tables and other data structures. So I still have some questions. I'm still not sure if I should be changing the ref count on any of these things. I kind of don't think so. I've currently am thinking that it's mostly about whether this thing is in the page free list. Maybe this check function can help me understand at the bottom. Oh, what? What? They're like, what? Checks that the pages are reasonable, but they do some weird stuff. Wow. Okay. The loop. Okay, going through the list. Page to P. So PP is a page info struct. Page to PA takes the PP minus K page. Why don't I get this? Page to PA. Is taking a page infrastructure and subtracting K pages from it. So that does not immediately make sense to me. Trying to understand. Oh, wait. Oh, wait, I think I see. Is that just like some being clever or something? So, but wait a sec. Yeah. Oh, okay, wait, now I see. Okay. So it's taking this pointer, subtracting, this is the K pages pointer, which always points here. Kanak, hey. Thanks for, I hope I said your name right. Thank you for tuning in. K pages always points to the start of this array. So therefore, basically we're computing the index of this entry into the array. And from that index, we can directly derive the physical address. Okay, that makes sense. So it's checking that. Okay, basically that answers my question. There are things that should not be in the list. And that's what it's checking. So, okay. So I need to modify this, or was it? So things should like literally just not be in the list. But also that function was kind of check. So what are the checks? So obviously we need to have a list. There's some Boolean or whatever, okay. There's that weird thing where it like writes data or something. Okay, it like corrupts memory or something like that to intentionally cause a failure if the list is wrong. And then lastly, this is the main one. Okay, yeah, which I was just looking at, but it's like, okay, these things should not be in the list. So for every single one, assert that it's not 0, it's not this thing, it's not some of these things. Assert that it's less than this thing, or I don't know what this really means. Page to kernel virtual address. Don't really know what that means. And it's asserting that we need to have at least one of both kinds. Kanak asks, how do I suggest Apple Silicon Macs for kernel development? No, it's a good question. So far, it's been pretty fine for me. I mean, I'm just running things in QEMU, and QEMU works well on them. I've had to do a little bit of things to fix the build sometimes, but it's like totally fine for me. I'm using this tool chain called, what's it like? It's like I386 whatever, with all the, the tool chain totally exists for it. So I'm having no issues at all with it. It's asserting that we need one of at least one of each type, at least one thing that's below this xfsmem, and then one thing that's above it. I don't like totally get what that means, but okay. Let's get back to this though. I think I kind of know what I need to do now. There's certain things that just should not be in there. All right. Give me 1 second. Right, yeah, like there's like certain things that are in the list that should just not be there. Let's start easy. Let's start with number 1. Physical page 0 should not be in the list. I mean, also what I'm thinking about right now is like, okay, say we like adjust this to not have everything be in the list. So for example, I think this will be like this, then, we're gonna, but then what happens with this thing? Does it ever matter that we just like don't have any pointer to this anymore or something? I don't really know, but let's just take it step by step and do the first one. Mark physical page 0 as in use. So we have like our normal code that runs. If one of the pages is actually legitimate, we run the normal code. Then maybe we can have some exceptions, like if I'm just gonna do this the dumbest way possible. If equals 0. Although I kind of feel bad about, I kind of feel like I want to make a constant out of this. Const int, call it like k0 page index. I don't know if that's being too much. I equals k0 page index, just to kind of avoid all these magic numbers. Eventually, maybe it'll be like some kind of array. I don't know. Just for starters. So, like, what does this, like, let's say I wrote this code. What happens? Does this do what I want it to do? So, going through all these things. Okay, if I equals 0, continue. We do not change anything. Maybe I'll just delete all these lines. So, next iteration, I equals 1. This does not run. Then k pages I, okay, so that's this 0, whatever. pp, so this thing is pointing at null to start off always. Then it basically just like does that, and then does this. So, I mean, I kind of think that's right so far. That's like the correct way, I think, to exclude things from the list, because eventually this is going to produce the same shape we originally looked at. So I think this general method of just simply not executing this code is solid. Yeah. So okay, so I think I think I kind of did it. Mark physical page 0 as in use. I think that, yo, Parth, what's up, man? Glad to have you here. Okay, the rest of base memory is free. It's free, okay. Which means it's totally eligible to be included here. So I think that's legit. Then comes the I/O hole. I kind of wish I knew what the I/O hole is, but I mean, maybe we can even learn about this. I/O fizz at 640K. There's a hole for I/O. After the advice on Discord, started learning Rust. Awesome. Glad that you're learning Rust. That's cool. What kind of stuff are you working on with it? Or what have you tried so far? The whole ends. Physical address. Ext. No. Word. Okay. Let's try this. So now our next thing is like if 0. I'm gonna also call this frame. That's kind of the terminology. Following the Rust book, checking out some open source Rust projects. What an amazing language. Nice. Very cool. Yeah, I would love to learn Rust someday, but I can't ever seem to just get away from C and C++, it seems. But yeah, one day. So I'm going to call this IO fizz mem start frame index. And IO fizz mem and frame index. Fizz mem. And what I'm trying to do here is just page size, page shift, I think. Because I need, like, I'm operating in terms of frame indexes here. I don't know, dude. C and C++ devs always say C and C++ are the best things that ever happened to them. That's definitely funny. I would not say that is true for me. I use C++ every single day at work, basically, and I cannot say that I love the language, but I will say I have grown to have respect for the language, because it is very powerful and you can write great code in it, but there's a lot of things you need to be constantly watching out for. Page. Yeah, 12 bits. Yep. Okay. Yeah, Linus Torvalds says C is the best. I mean, yeah. Personally, I think C is okay, but I'm planning to port all of this C code to C++ eventually. There's just, yeah, I think C is just the bare minimum, basically, in my opinion. And there's, I mean, obviously, there's a lot of downsides to just having only the bare minimum. But 20-second break. Okay, so now I got my, so I'm basically converting what are these physical addresses into simply just the indexes by shifting off the low bits. So now I'm like, if I is greater than or equal to KIO, or I is less than KIO phys mem end. Continue. This is kind of gross code. Like, I'm not very proud of this code, to be honest, but I'm not really trying to write the cleanest code right now. So I think this should roughly be doing what I want. I'm trying to exclude. Oh wait, but wait a sec. I need to think this through a bit more. It might be right, but I have not thought about what happens when we like skip one, then have a bunch, and then skip some more. So let me just do that real quick. So let's begin our simulation again. Page free list points at null. Okay, we're at I equals 0, in which case we continue and do literally nothing. Next one, I equals 1. We go set the link to where this thing points, and then kind of like swap the pointers to wherever we were. Now let's pretend we do that one more time. So this thing points here, and we swap the pointers. Now that simulates this whole region. Oh, what? Oops, I did not mean to do that. Okay, that simulates this whole region of like actually adding things to the list. Now we're in the IO hole. Let's figure out what's going to happen. So let's say we're in the IO hole, and I'm just going to have like a sticky to represent our current like iteration cursor. So we're at like 1, 2. Now we're on this next one, and let's say this is the start of the IO hole. Now we're going to be like, okay, if this is in the IO hole, continue. So we're going to literally do nothing and move to the next one. Let's say we're also still in the IO hole. We do literally nothing. Now let's see what happens. Okay, so now we're out of the IO hole. We don't continue, and we set the ref count to 0 or whatever. Set pp link to wherever the page free list was last pointing, which is like right here, and swap the pointers. And to me, that looks correct. It's like not super obvious to me in the way this line of code is written, but basically this is saying set us to point at the list head and then reset the list head to like our current us, like the current iteration thing. So yeah, so this illustrates we skip the first one, do a bunch of stuff, have the IO hole, have the non-IO hole stuff, and I think this works. So I'm gonna call that good. Let's keep it moving. Only got a couple minutes left, 12 minutes left or so. Then extended memory. This is probably the hardest one of all 4 of them. External physical mem. I don't know. It's like the rest. Some of it is in use, some of it is free. Where is the kernel in physical memory? The kernel is at like 1 megabyte, I think. I'm pretty sure the kernel's at 1 megabyte. Which means it's not free. Interesting. I mean, yeah, kind of just to copy this over or whatever the boot elk So we were also actively using, I'm just gonna scooch up this thing. So we have been actively using the boot alloc region so far. So the question is, I mean, like none of this is free. That's really the point. Also, I didn't need to refresh on these numbers. So it's what is it? 640K. There's an IO hole, and it ends at 1 megabyte. Okay, where our kernel starts. That's very convenient, actually. Yeah, our kernel starts. I don't know what this thing is. What is that thing? Whatever. Excuse me. But very clearly, there's this thing, and then also from the oh, what the hell? Sorry. Wait, what? My oh. I have caps lock on. I think that's what screwed up. Okay. Sorry. Read elf. Elf. Yeah, physical address. 50 is 1 megabyte. So the point of that is just to clarify what. Okay. So the kernel is at 1 megabyte, which is conveniently where we stopped. K kernel start frame index 3, 4, 5. Do we have a variable for this? I feel like it would be good to have one. I kind of want to add one. Oops. I'm taking the opportunity to introduce my new naming convention of not just using all uppercase with no separation between the different things there. Okay. K kernel physmem. Although, I mean, it is kind of the same thing as this thing. I'm currently debating if I should just make them equal to each other or if I should keep them separate like this. I think I'll just keep it separate to start. Okay. So K kernel start from index. And then here's kind of the funny part is, where's the kernel? Which pages are already in use for page tables and other structures? Well, it's just all of the kernel. Like the implication, I mean, everything, all of the kernel is in use. Like later we're going to use this free list to allocate memory probably, and then write stuff in there. So we don't want to be accidentally including our kernel in the free list, then later trying to get some memory right to it and like corrupting our kernel. Nicholas, if I understand correctly, this is for keeping track of page and used pages. Yes, this is for tracking the physical frames, the physical memory frames. Like we have, this is my illustration of physical memory. We have like this whole region of physical memory, 4 whole gigabytes to like dish out later when we need to dynamically allocate memory. And so we're trying to make some data structures to track this and track which of these are used or not. And the way we're doing this is we have a struct that represents each 4K page or 4K frame, as it's also called. So we're dividing this whole thing up into chunks of 4K bytes. We have a struct for each one of those. And then we're having a linked list of all of the free ones, because apparently you might need to like know which pages are free or something. And so you go to the free list, get the first one, and pop it off the front of the list or whatever. That's my understanding so far. I don't totally know exactly how we're going to use this, but that's what we're doing right at the current moment. And so I can easily just say, okay, I mean, I know that the kernel starts there, so that's pretty clear that that is not going to be free. The question is, yeah, no problem. Yeah, please feel free to ask any questions if you have them too. I'll be happy to try to answer them, and maybe it'll help me understand something better too. So we have the kernel, and it like ends somewhere. Well, actually, we know precisely where it ends because of our extern char end thing, I think. Because we have that symbol, actually. So that's actually kind of cool. And we can actually use this to like kind of find out where the end of the kernel is. That's kind of nice because the size of the kernel is going to change as we literally add code to the kernel. And so it's not going to make sense to be like hard coding how big our kernel is. So it's kind of nice that we have this symbol there to find out the end of the kernel. And I believe it is I believe it is page what? Oh, whoops. Wait, can I... Do you know the size of the kernel at runtime? Should this be dynamic? I mean, the kernel binary doesn't change size at runtime. Yeah, I think this should be a pretty safe bet. Where's the kernel? Which page? For page tables and other data structures. Page tables. Okay, yeah, so the boot page tables are like in the kernel binary already. Like we statically construct them at compile time. We have this new set of page tables that we just allocated with boot alloc just before. So that's a separate region we will need to exclude. So I think I got this. The question though is, what is this end thing? The boot alloc, I kind of just want to next. You gotta be kidding me. Okay, yeah, end is this interesting. It's like totally not aligned, which is of course like the reason for this thing. So we can I'm just gonna like hack it. Like, okay, so we have kernel. I don't even know. Round up, and I'm basically copying the same code from over there. Page size, right? And so that's actually the first thing that's like not not part of the kernel. Technically, this is the part of the boot allocator zone now. Kernel and virtual vadder. So we have this kernel and vadder. And then now we can have our kernel end frame index, which is going to be our kernel and vadder page shifted over. And you probably can't shift a void pointer or something. Or I probably need to cast this to uint pointer t. So now I have like the kernel region, and I'll do the same kind of thing. K kernel start frame index, or K kernel, kernel end frame index. Omit those also. In IoT, we hardcode sizes in the bootloader. Interesting. Hardcode sizes, like what kind of sizes? Like the size of the kernel or something? What kind of IoT stuff are you working on, Nicholas? Okay, gotta... Can I finish this? Just... Okay, so now we have this. And the actual final thing we're going to need to do is then also mark the boot alloc zone as non-free. K boot alloc start frame index, and that's going to actually be K kernel end vadder, and then we're going to have K boot alloc end frame index. And actually, to find this, it's going to be boot alloc end vadder, and we're actually going to use that thing that we did in the boot alloc, that feature we built, where if you pass 0, it just returns the next free slot. Yeah, because we actually kind of need this to then later do K boot alloc and v address. Is that right? Also, what happened to this thing? Why is there a fuzzy line? Oh, okay. Okay, massive question. Does this build? Does this even build anymore? Q. Bake. It builds. Really? I'm just gonna add a dumb thing. Did I really? Yep, okay, cool, it builds. And I also, okay, now I need to do this. So there's obviously way better ways to do this. Okay, boot and frame index. 15-second break. Be right back. All right. Yeah. If I is greater than equal to, so the same pattern of basically just having these two pairs of variables that represent the start and kind of like one past the end sort of thing. Kernel end, the start frame. That's rounded up to the page size. I mean, we could even just set, and we could even just k kernel and frame index, because we know they are contiguous. And then, yeah, we kind of dynamically query this from the boot allocator and determine our end. And then we just kind of rip through the whole thing, skipping what we need. So I don't know if this is right. I don't really know how to check. I'm a hopeful. And now I want to jump to a symbol, page. No, I want, it's like the mem init thing. Okay. Moment of truth. Moment of truth, everybody. I'm going to officially attempt to execute check page free list. And we will see what happens. Well, actually, the first thing I'm going to do is I'm actually going to intentionally make it fail. I'm going to skip this check. So just to make sure everything's working, I'm going to intentionally include the 0 frame in the list. Just so we can test. What? Page free list is a null pointer. Holy, what? How is that possible? Are you serious? Am I? Okay, maybe I did something extremely stupid just now. I could have, apparently this is never getting called or something. Okay, yeah, I'm gonna hit the debugger once more. Page init mem init page init continue. Okay, let's step in here. Let me just quickly inspect all of these variables, which I have set and I like thought were right or something. Let's just sanity check some of this stuff. PK0, right? IO fizz mem start. Is that right? Okay, that seems wrong. it, wait a second, what is it? I was trying to strip off the low 12. Wait, okay, did I totally do this wrong? Oh, hex. So it strips off the 3 0. So hex. Okay, I think that's right actually. So hex A0, and then this next one. Is 256, which is hex 100. And then what? Just for fun, I'm just gonna print this optimized out. Okay, ouch. Okay. Then this is what? Optimized out. Sheesh. Interesting. So, why did that just stop? Okay, time to add some printfs. I'm just gonna do the dumbest test. Are we even running any loop iterations? Or maybe, or what? Why is that? What's happening? Why is it like pausing like that? Quit. Yeah, it's pretty obvious I have a very embarrassing bug right now, because apparently this is not running any of the loop iterations. Oh wait, okay. I think I need ands here. Yeah, that is embarrassing. Always gets you. Yeah. I want it to be if it's greater this thing and less than continue. Otherwise, obviously, it's just gonna, I don't know. Well, I think that's pretty clearly a bug, but I kind of would have still expected it to, okay. So now I'm like actually running the loop, which seems okay. Weirdly, I feel like it stopped way too early. It's like N pages is huge. It's like 32,000. So I kind of have the sense something is really going wrong, but whatever. At least my initial test worked, where it's like failing there. So now I have this other bug where apparently I never got past external memory, which is very annoying. Like, man. So obviously there's some bug here. Somehow it got all the way to the end though. And it's failing on this XML one. Because apparently this never ran. It's for everything. Well, I think it's pretty cool. Like, it's super suspicious that this thing stopped. I'm just gonna do an assert 0, which is my classic trick for making things stop. Yeah, I feel like it stops running way too early. Size T or whatever. Yeah. Yeah, and pages is so huge. I mean, realistically, I should just be like printing all of these things out, I think, to sanity check them. This is so annoying. Okay. Kind of want to define a macro that generates a print statement for me. Define it's called xprint. It's gonna be cprintf. I do not know how to write macros well enough to do this. This. I'm just gonna take a wild swing at it. Print. And I'm just gonna try to print out something easy like K0 frame index. And maybe KIO start. Just out of curiosity. Does this even work? Nope. How do I actually I need to ask ChatGPT. How to write a macro that takes a variable and printfs it while printing the name of the variable and its value ints only. Oh, really? What? To interpolate the variable name into the string. Fuck. Strong. Whatever. Okay. I feel like there's another way to... Wait, what? Is this even right? String literal. Oh, I see. Maybe I could just do this. Let me try that. Yeah, there we go. But I kind of thought I already verified a lot of this stuff, so. Okay. Start frame index. End frame index. Boot end. Ugh, book end. End. Okay, doing some debugging. Yeah, okay, so clearly these numbers are way too big. Kernel frame, why is that so big? That's my problem. This thing is way too big. Maybe it's because of this dumb thing. Oh, wait, what? Oh, because it's a virtual address, duh. Sheesh. I need to convert that base to a physical address, and probably the same thing for this thing. That's why it's so stupidly huge. One more time. All right, now this is gonna take absolutely ages. Now I'm printing out, I mean, it's gonna take until like 32K, or I mean, it's like halfway there already. I don't even know how to stop it. But that is like a better indication that things look right. Sheesh. Okay, good. Now let's see. Yeah, I think that's correct. Man, I need to. Now it's time to stop printing that out and take away this and try one more time. What? Build what? What happened? Why is this not working? What happened? Did something? How did this? Somehow all this stuff got reverted, because I must have like done that somehow. Okay. Last time. Panic, the function is not finished. But, notably, I think it didn't panic in that checker function. Like I, was it check page? This thing was called, right? Check page free list. So I think I survived. I got through this function. It didn't assert. So I'm going to call that a win. I'm going to call that a massive win. And I'm going to end the stream because it's been 2.5 hours. Gotta go make dinner. But thanks so much for watching. I'm just going to plug myself real quick. Like, yeah, if you like what I'm up to, like, comment, and subscribe. You know, please feel free to join my Discord. I'll share that link. Would love to have you in the Discord. Yeah. Rome wasn't built in a day. So true. I feel pretty good about this this work session. Like this was like every session I write a little bit more and more code. And I'm taking on the things I really just don't know. And so I would call that a win. We did not even finish the exercise, but we'll continue with it next time. I might stream tomorrow, actually. I have the day off tomorrow, so I might stream. But I'll stay up. Like if you join the Discord, I'll keep you updated with when I stream. But usually it's just every Sunday at this time. I think that's it. Yeah, thanks a lot for joining, and I'll see you next time. Peace.